Answer for 498. Yes, it is B. Yesterday I've told you, na, this one I've explained. For this pipe flow, the average velocity occurs at R equals to R by root 2. This I have already explained yesterday. You should remember this particular thing. Okay, so the answer for this one is D. Okay, you can solve this question. So discharge formula. Discharge will be what? Q is equals to area multiplied by average velocity. So this will be pi r square multiplied by average velocity, which is this one, r square by 8 mu minus dp by dz. So discharge and viscosity, how is it related? Directly proportional or inversely proportional? So what should be the answer here? So answer should be D here. Okay. Next question. This one. See, shear stress. Yes, 0 at the center and varies linearly with radius. Correct. This shear stress, it is 0 at the center and varies linearly, and maximum at the wall. Maximum at the wall and 0 at the center. So 0 at the center and varies linearly with radius. Okay, this is related to boundary layer. Boundary layer question will see after some time. Question number this 449. Velocity profile, it is asking. Velocity profile for flow between two fixed parallel plate. Check how the velocity varies. Yes, parabola. It is C. varies parabolically across the section. Yesterday only we have seen, no, if this is fixed plate, this is also a fixed plate, then the velocity varies parabolically. It is maximum at the center and zero at the wall. So C answer. 408. Yes, velocity of fluid particle at the center of the pipe, it is maximum. Correct. Okay. Now next we'll start next topic. Next topic is laminar boundary layer over a flat plate. So you see, till now we have uh, studied about flow in a closed conduct, or like flow between two fixed parallel plates. In between these two fixed parallel plate, the fluid is flowing, or through a closed duct, the fluid is flowing, or through a pipeline, a fluid is flowing, like this. Okay, viscous fluid. Okay, now we'll study when the fluid is flowing over a flat plate, a single flat plate. Like this is a flat plate. Over this, the fluid is flowing. Okay, now again we'll try to derive the equation for flow over a flat plate. Okay, flow equation of motion for flow over a flat plate, or the momentum equation for flow over a flat plate. And then we'll combinedly will solve flow over a flat plate problem. Combinedly means the combination of two equations: conservation of mass and conservation of momentum. Okay, so see what happens. Let's say initially the fluid is entering at this section. The fluid is at this section, actually the fluid is entering with uniform velocity. Okay, in y direction, every point, if you see, the velocity is same, uniform, u infinity. With this velocity it is entering. Okay, at the entrance here, at x equals to 0, it is entering with uniform velocity. Now after that, what happens? No, due to no slip boundary condition here at this point, at any section, we can talk about any section. Let's say the fluid at this section. This section we have completed. Okay, now we'll talk about fluid at this section. Now at this section, at this x, as the fluid is in contact with the wall and wall is stationary, so velocity will be what? 0. So here the velocity will be 0. Now as this velocity is 0, it will try to stop the immediate layer above this one. Now this will try to stop the immediate layer above this one. This will try to stop this one. This will try to stop this one, and then further. But the effect in this direction, it will be lesser. Okay, it will reduce. And a moment will come when the effect of stopping the stopping of this layers will be very less, and a point will come where this effect will be negligible, like the velocity at this point. Okay, with the velocity at this point will be 0.99 times the free stream velocity, the velocity with which it has entered. Okay, so you see here the velocity is 0, but as this is 0, so this will try to stop this layer, but this is having some velocity, so it will move with some velocity, not with 0, but a little more than 0. Now this will try to stop this velocity, but as this layer is having higher velocity and this is lesser velocity, so this will move with a velocity which is in between these two. Similarly, in this direction, what happens? The velocity will increase. Here it will be 0. It will increase, and finally a point will come where the velocity will be equals to 0.99 times free stream velocity. Beyond this point, every point, if you see, velocity is beyond this point, velocity is equals to free stream velocity only. Okay, u is equals to u infinity. So this point, this particular point is noted here. Okay, now at any section, if you see, if I take this section, same thing will happen. A graph will a velocity profile will come like this, and at this point the velocity will be 0.99 times free stream velocity. If I make the plot here, here also we'll get velocity profile like this. Here it will be 0, it will increase, and a point will come where the velocity will be 0.99 times of u infinity. So when we'll join all these points with where the velocity is what, 0.99 times free stream velocity, then this particular layer is known as boundary layer. It is forming a boundary between what? So inside it is a boundary layer. Okay, this is forming a boundary. Okay, this is forming a boundary. Inside layers are inside boundary layer, and inside it is means inside the flow is considered to be viscous flow. Okay, so what you are asking? Yes, between fluid layers, between like this layer and this layer is there. Here the viscous effect between these two layers can be noticed. Okay, can be seen. But when you are going above this layer, no, if you're considering two different layers, then there will be no viscous effect seen in these two. Like, see, friction can be seen when two bodies are moving. Let's say these two bodies are moving, then between these two only, and if these two are moving with a different velocity, let's say this is moving at 2 meter per second and this is moving 1 meter per second. So, or this is moving with 4 meter per second. Then as these two are moving with different velocity, there will be a friction between these two. It will be noticed. But if two bodies are there and both are moving with same velocity, 2 and 2, then between these two at the interface, you will not notice the friction, because both are moving with same velocity as a as a single body. It is moving as a single body. Okay, so same thing is a similar thing is happening here. Beyond this layer, what happens? This is our boundary layer, and beyond this layer, two layers are moving with same velocity, so the friction effects are not seen between these two. Okay, so viscous effects are not seen between these two layers. So with this, what we are concluding? We are concluding that the two very important points we are concluding related to what? Laminar boundary layer over a flat plate. Okay, laminar boundary layer over a flat plate for any flow where this laminar boundary layer is forming. Two conclusions. One is, inside this boundary layer, viscous effect is significant. So near to wall it is maximum, away to wall it is reducing. Here it is almost zero. Beyond this, the viscous effect is zero. And if viscous effect is zero, that means shear stress between these two layer will be what? Zero only. Shear stress tau between these two layer will be what? Zero only. Because if two layers are not moving, there is no relative motion between these two layers, then how come there will be a shear stress? No. So like shear stress is what? tau goes to mu du by dy. So du by dy. So velocity of these two layers are same only. So du is what? 0. So shear stress is 0. So shear stress outside the boundary layer is 0, or viscous effect is 0, or the third point is the flow is irrotational. Okay. So again, I'm telling you, you can note this point. Outside boundary layer, flow is inviscid, okay, inviscid, or viscous effect is negligible, shear stress is 0, and flow is irrotational. And if flow is irrotational, then we call that flow as irrotational flow as potential flow. Okay, so outside the boundary layer, you can note these 4 points: inviscid, shear stress is 0, irrotational flow, and it is potential flow. Now inside, if we talk about this inside boundary layer, fluid is viscous, flow is viscous, shear stress is significant. It is significant shear stress it is having, and it will be maximum at the wall. Shear stress will be maximum at the wall. Okay, and it is rotational flow inside. It is having rotational flow. And if you talk about potential, if it is rotational, then it is not a potential flow. It is not a potential flow inside. Okay, so these points you can note inside the boundary layer. Okay, now next is you see, this is the boundary layer, and this height represents the thickness of boundary layer at any x location. At any x location, this represents the height of your boundary layer thickness. So you see, it is keep on increasing with in which direction? X direction. Okay, so the boundary layer thickness, which is delta, is function of x. Okay, so boundary layer thickness is function of x. It is 0 at this point, and it increases in the flow direction. So this point also you can note down. And one more thing, the velocity variation in y direction. So here, velocity variation in y direction. What it is? Velocity variation du by dy. Velocity variation with in y direction. It is what? 0. Outside the boundary layer. Well, because du means this is also same velocity, this is also having same velocity, this two layer. So change in u with in y direction, it what? Du by dy, what it is? It is 0. In y direction, the velocity change is 0. So du by dy is 0 outside the boundary layer, this point. Outside the boundary layer, du by dy is 0. Inside the boundary layer, du by dy is significant. Okay, or dou u by, because u is function of x and y both, so dou u by dou y is significantly higher than velocity variation in x direction. So inside the boundary layer, velocity in variation in this direction, x direction, is not that much. It is varying in x direction, but it is not that much compared to variation in y direction. Okay, so this point also you can note down, that inside the boundary layer dou u by dou y is very large, means it is larger than dou u by dou x, but outside boundary layer dou u by dou y is 0. This thing you can also conclude with the explanation what I have given earlier, but okay, I'm just specifically telling you this, you can note out. Let me know when you are done. Okay, now in viscous flow in a pipe, we have seen two forces were significant. One was pressure force, force due to pressure, and another was viscous force. Okay, these two forces were significant, and these two only we have considered while deriving the equation for deriving the equation of means like momentum equation for fluid flow in a pipe or between two fixed parallel plate. Now flow over a flat plate. Now if flow is over a flat plate, here again, see, this is our two-dimension Navier-Stokes equation. Okay, two-dimension Navier-Stokes equation. Now again, you cannot solve this two equation. It is very difficult to solve this two equation. So it is better to neglect few of the terms. Okay, so with the help of non-dimensionalization, first we'll non-dimensionalize the equation, and then with the help of order of magnitude analysis, we'll try to neglect some of the terms from here, as we did in fluid flow between two fixed plate or Cotte flow, and then we'll solve that particular equation. Okay, so to do that, first we'll have to non-dimensionalize. So this is the u is the velocity in x direction. In y direction we have velocity v, and we free stream u infinity. This is the free stream velocity, or the velocity with which it is entering. So to non-dimensionalize it, you will have to divide any particular variable with a constant which is having same dimension. So velocity should be divided with velocity only. So u we can divide with u infinity. V again we can divide with u infinity, because u infinity is our reference. We know the value of u infinity. That's why we are dividing with this one. So now this will become our new velocity, which is u star. U star is u by u infinity. U by u infinity, which is u star is your non-dimensionalized velocity in x direction. Similarly, you will have v star, non-dimensionalized velocity in y direction. Now similarly, you can non-dimensionalize pressure as p by rho u infinity square. Rho u infinity square will have a dimension same as pressure. That's why we are dividing it with this one. Anyway, we have dynamic pressure. The equation will be half rho u infinity square. So this is dynamic pressure. Okay, so that's why this 1 by 2 is constant only. So this term we have taken for non-dimensionalizing this one. So p by rho u infinity square. Now x we can be non-dimensionalized with the length of the plate. If this is this length is L, and we have taken coordinate as this as y and this as x. So x can be divided by length L and we'll get x star. Y can be divided by L and we'll get y star. Like this, we can non-dimensionalize, and we can put u equals to u star into u infinity v star u again this is v actually v is equals to v star multiplied by u infinity. Like that, we can put here every term. When we put here, no, our new equation will be reduced like this. And while doing this, a factor will come here, which is Reynolds number. Okay, Reynolds number. Now you see Reynolds number. What it tells? It tells us the relative magnitude of inertia force and viscous force. So in this particular case, we'll try to neglect few of the terms and then we'll try to solve the equation. So first, after non-dimensionalizing, we got this two. This is in x direction. This is my continuity equation, and Re is what? Rho u infinity, which is velocity, multiplied by length of the plate and divided by mu. Rho u L by mu. This is Reynolds number in case of flat plate. In case of pipe, in case of flow in a pipe, the Reynolds number is rho u infinity multiplied by diameter divided by mu. There it is diameter of the pipe. Here, that this particular thing is length of the flat plate. Okay. So here you don't have to note anything. You don't have to remember anything actually. You just have to notice that Reynolds number is defined like this. Okay, this is the Reynolds number. See, I have told you because after this is the Navier-Stokes equation which I have already explained. But from here to here, if I would have directly told you, no, there would have been some confusion where from this Re is coming. Okay, so this Re is coming after this non-dimensionalization. Okay, and adjusting the constant terms, this Re is coming here. Okay, so these two are the new equations. Okay, now in order of magnitude analysis, what we do is we just check which terms are not comparable or which are very less. Okay, so you see like which is having a higher value, we can give it 1, and which is having very low value, we can give it as epsilon. Last slide. Which is having higher value, we can give it as 1, and which is having lower value, we can give it as epsilon. So now velocity, the velocity in this direction, u star, it is significant, so we can give it as 1 because in this direction fluid is flowing. Okay, so it is having significant velocity. Similarly, in this direction only, if it is flowing, x can be regarded as larger only. Okay, this x direction, it is very large in this direction, so that also can be given as 1 value. But y direction, which is the direction of boundary layer, like if I take the example of this thing, if I consider this particular figure, you see the dimension of, or the height of this boundary layer, no, which is in which direction? Y direction. It is very less compared to the length of the plate. If this is my length of the plate, and let's say if it is 1 meter, this height will be in mm. Okay, in mm, very less. So y direction, because we are focusing inside this only, not going outside. Outside again, you can go up to whatever height you want. Okay, means how much up to what height the fluid is flowing, you can go. But we are just talking up to boundary layer. So you see the height of my maximum, let's say the maximum height is occurring somewhere here. This height itself which is in y direction, will be very, very less compared to your L. This y, when you will solve the questions, no, we'll see that y value is very less. It will be in mm. But L, the length of the plate, it can be 1 meter, 2 meter, like that. So this y is very less. So we can give y as epsilon. Okay, this y we can give epsilon. Okay, its value is very less. Now we'll do the order of magnitude analysis. Order of magnitude analysis. So u star value is 1, x star value is 1, y value is very small. To get this value as if I want same this thing, like so that I can cut this to value, and both the terms should have same order of analysis, same order, like if this is 1, okay, then this also should have similar order, then only I can get this value as 0, okay, in opposite direction. So if this is epsilon, this y is having order of epsilon, then v star, the velocity in y direction, v star will also have order of epsilon, very small order. So the velocity in this direction, v, will be less, very less compared to your free stream velocity, or even your u star also. Okay, so this is the first conclusion we are making here. You don't have to remember this one, you just try to understand. What you have to remember, I will just tell you after this slide. So first conclusion we are drawing from here is the velocity in y direction, it is of epsilon order, means very less order. The first conclusion we have drawn with the help of continuity equation. Now we'll come to momentum equation in x direction, momentum equation in y direction. Now momentum equation in x direction, u is 1, this u is, you see this u is 1, x is 1. Now v is having order of epsilon, u is having order of 1, y is having order of epsilon. Okay, so this 1 1 1, so overall order is 1. Epsilon epsilon we can cut, so we'll have our order of 1 only. Dp by dx will keep for some time. Okay, now next is here, if you see Reynolds number, Reynolds number is very large. Okay, so 1 by Reynolds number, because Reynolds number is the formula of Reynolds number is rho u infinity. So this L is very large, u is very large. So 1 by, see, this is having order of this having very large order. This is also having very large order. So 1 by of that will be very less. Okay, so 1 by epsilon. So this is having epsilon square. The Renault 1 by Re is having order of epsilon square. This is having 1. This is having 1. Okay, this is having 1, but this is having epsilon square. Now if I multiply this epsilon square inside, this will become what? Epsilon square. It will be square by epsilon square, which will give 1. So you see this term is having order of 1. This term is having order of 1. But this term, anyway, we have not seen anything for this one. We'll move to this one. Here you see it is having order of epsilon square. Epsilon itself is less. Epsilon square will be further less, like 0.2. Square of 0.2 is 0.04, further less. But this is again epsilon square by epsilon square, which is 1. So this term is having order of 1. So you cannot neglect this term. See, this, why we are doing this one is, see, you have to solve this particular equation. You want to solve this particular equation. Now you are doing some project, and there are four participants, like 1 4. Now if someone is not contributing in your project, then you should neglect that thing. You should neglect that thing, you should neglect that person and move ahead. If someone is only contributing 1% or less than 1%, why to uh, uh, take a headache, or why to consider that person itself? Leave them behind and move forward. Go ahead with your 99%. You will get some means only 1% error you will get in your this problem. So just now with this order analysis, we have seen that this is having order of 1, this is having order of 1, but this is having order of epsilon square. That means this particular term is not at all contributing, means it is contributing but it is very less. So we can neglect this term. This term, it is having significant like epsilon square by epsilon square, so it will become 1. So this is having some means it is having contribution, but this term is not having contribution, so we can neglect this term. So I have told you this thing because I could have from like our this equation, I could have written directly like this, but you would you will get confused. Like, sir, how you have written this equation? How you have arrived at this particular equation? So this is the reason I am neglecting this particular term. So we are left out with 1, 2, this 3, and pressure wala term. So we have 4 terms now. One term we have neglected. Okay. Similarly, if we do order analysis in y direction, this will have, see, 1 1, and this v is there, so it is having order of epsilon. So 1 1, so it is having order of epsilon only. This epsilon can cancel out, still order is epsilon. This term, okay, we'll see afterwards. Reynolds number, it is having order of epsilon square. This is having order of epsilon. This is having order of epsilon by epsilon square. Now, if I multiply inside, you see this is epsilon 0. Order means its contribution is very less. This is having contribution like near to very 0. The value is 0. Now, this if we compare this to, like, first I will have to multiply with this epsilon square. So epsilon square multiplied by epsilon, so is epsilon cube. So again the value is very less. So this also we can neglect. Similarly, if I multiply here, still I will left out with epsilon. Okay. So all the terms here, the y component of momentum equation, it is not at all contributing in fluid flow. It is contributing, but their contribution is very less. So all the term we can neglect, and we can go ahead only with this term, which is minus dou p by dou y, which is equals to 0. Now again, dou p by dou y, which is equals to 0. What it is telling you? Dou p by dou y 0 means pressure gradient, pressure is not varying in y direction. Pressure is not varying in y direction. Okay. So this is the final equation for flow over a flat plate is this thing. Okay, this is the final equation for flow over a flat plate. So you don't have to remember this equation. Okay, anyway you can remember, because means if you want you can remember, because now it is easier, because if you can remember Navier-Stokes equation, you can remember this also, but don't have to actually for HAL, so not at all. Now here if you see, the first conclusion we are drawing here is that pressure is not varying in y direction. For I'm talking about what? Flow over flat plate. So first point you can make a note that pressure is not varying in y direction. Okay, this is the first point you can note. Now second is pressure is function of x only. If pressure is not varying in y direction, here it is this particular term is dependent upon all these things. So you cannot say pressure is not varying with x. It is varying with x. Okay. So pressure is function of x only. Okay. Pressure is function of x only. Pressure is not function of y. Pressure is function of x only. So this is the conclusions with respect to x, with respect to pressure. Okay. Now, as the pressure is varying only in which direction? In x direction and not with y direction, you can find this pressure gradient going outside the boundary layer, apply Bernoulli sequence outside, and you can find this particular thing. Okay, you can find this particular thing if you want. Okay. Now so the first conclusion I have already told you. Okay. Now next conclusion which I am going to tell you is, means next thing what we are going to study is the Blasius flow over a flat plate. See, Blasius, what he did, he wanted to solve this particular equation, this differential equation. So for that he did all these assumptions. First he made all these assumptions, then he reduced some of the variables, and then he found one equation which is known as Blasius equation, and then he tried to solve that equation to get velocity, to get shear stress, to get friction force at the plate, like that. These things he actually found. Okay, so the another point which we are going to conclude from here is that Blasius found that after applying the this Bernoulli's equation outside the boundary layer, he got this equation. He got, from which he can draw that rho is constant, u, then this term itself is constant, and right hand side also is constant, then this has to be constant. If, see, p plus half rho u infinity square is equals to constant. He got this equation after applying Bernoulli's equation outside the boundary line. So density is constant, u infinity, it is constant only. This is the velocity with which it has entered. U is the variable velocity, but u infinity is a constant velocity. So this term is constant. Right hand side is constant. Then this has to be constant, na? Otherwise, if this is variable, then how come this two can be constant? Not possible. So pressure has to be constant. Okay. So pressure is constant in flow over a flat plate. If this is constant, then if I take derivative of pressure with respect to x, it is 0. Okay. So remember, when we were studying the fluid flow over two fixed flat plate, there the pressure gradient was constant. It was not 0. It was constant. Dou p by dou x or dp by dx was constant. This term was there when we were solving our viscous flow in a pipe or viscous flow between two fixed parallel plate. Do you remember? This thing was there, dp by dx. Do you remember? This was there. The final equation itself, if you remember the velocity equation itself, there you can notice there was dp by dx. But here dp by dx itself is 0. So flow over a flat plate, in this case, dp by dx is 0 or pressure is constant. So in GATE 1 mark question, they have asked this thing. Flow over a flat plate, pressure is constant or varying, or pressure gradient. Pressure gradient means dp by dx. Pressure gradient is 0, pressure gradient is constant, pressure gradient is variable, like that option was there. Okay. So with respect to gradient, pressure gradient is 0 for flow over a flat plate. Pressure is constant for flow over a flat plate. This 2 point you can make a note. Which condition? Flow over a flat plate or for Blasius flow over a flat plate? Yes, pressure gradient is constant for flow between two fixed parallel plate. So Blasius found that dp by dx is what? 0. If dp by dx is 0, he can put this particular term itself is 0. If he can put this particular term 0, then he left out with only two term. This is your acceleration wala term. If I take this rho here, rho into acceleration, so mass into acceleration, which is inertia. This represents inertia, mass into acceleration, and this is what? Mu dou to u by dou y square, which is related to your viscous force. So you see, left hand it is inertia, right hand it is viscous force, and relative magnitude of this two, the ratio of this two only tells you what? Reynolds number, inertia force by viscous force. Okay, the relative magnitude of these two forces only tells you the explains the Reynolds number. Okay. Now again, what he did, Blasius, he actually reduce this equation with the help of some variables and the boundary condition. Like if this is my flat plate and this fluid is flowing like this, okay, like this, the fluid is flowing and this is my boundary layer, and this, at any location the velocity profile is something like this. So you see the velocity is varying like this. At this point, like at y equals to 0, velocity is 0. But at y equals to this, which is y is equals to infinity. Now, why we are calling it as infinity? Because it is very far away from your plate. That's what we assume. It's not like infinity means very large number. Very means infinity means it is away from your plate. That's all. It is very far away from plate. Far away from plate, if you are going, you are getting which region? Inviscid region, where u is u infinity, where y is infinity, u is u infinity, the free stream velocity. So these two boundary condition he has used. Okay, so you can note the boundary condition actually. You can remember the boundary condition actually. I will again write it for you. This is my flat plate. Okay, and this is my boundary layer, and at any location, if I am making this boundary layer, so at this location, now this is my y direction. So at y equals to 0, y equals to 0 means here, velocity is 0. This v also it is 0. At y equals to this location, which is very far away from wall. So y is equals to infinity. Y equals to this location. The velocity u is what? U infinity. Because it has reached to which region? Inviscid region. The velocity is u infinity. So this you can note down. Okay. So the boundary conditions for Blasius flow over a flat plate you can note down. So this is the equation. This is the boundary condition actually. Okay. Now Blasius, why he was doing all these things? What he wanted? He wanted velocity field within the boundary layer. He wanted boundary layer thickness. He wanted to calculate the thickness of this boundary layer. The thickness of this boundary layer at any location. He wanted to calculate. He wanted to calculate shear stress distribution. We have seen this also in last lecture. Shear stress variation for flow over a flow in a pipe. Okay, and drag force on a plate he wanted to calculate. Okay, now what he did is he wanted to reduce this number of variables with the help of stream function actually. Okay, with the help of stream function he reduced the number of variable. Okay, and finally he got this equation. Okay, you don't have to go with the derivation. Means that is not at all required here. Finally he got this equation. Here you have to remember that you have to remember the order of the this thing equation, and whether it is linear or non-linear equation. So Blasius equation, its order, because they have asked this was asked in GATE 1 mark question. They have already asked this thing. See what happens sometimes, what happens this PSU exams now, they ask questions from GATE, direct questions from GATE. Sometimes they ask. Okay, so and as this is a 1 mark means objective in this theoretical questions they are asking here. So the questions which they have asked in GATE, which is a theoretical one, that we should not leave actually. Okay, that though we should pakka solve. Okay, because sometimes they directly ask question from GATE. Okay, sometimes, not always. It is your luck only. Okay, so Blasius equation, what is the order of the equation? Its order is 3. You see, 3 dashes. So it is third order and non-linear. These two are multiplied, so it is non-linear equation. Okay, so you can make a note of this one, that it is third order non-linear equation. Okay. Then after solving the equation, he got shear stress formula as this. Okay, shear stress formula as this, which is 0.332 multiplied by rho u infinity square divided by root over rex. Now it is rex. Now when it is rex, then it is rho u infinity. Then instead of length L, you will have to put x divided by mu. See, x represent at any location. See, if you have a flat plate like this, okay, whose length is L. Now this is your y coordinate, this is your x coordinate. Now if you want to calculate, see, Reynolds number will vary in this direction. Reynolds number will vary in x direction. So if you want to calculate Reynolds number at any x location, Reynolds number at any x location, it will be rho u infinity x multiplied by mu. This is the Reynolds number equation. Okay, at any x location. And if you want to calculate Reynolds number, the average Reynolds number, then you can put REL, which is rho u infinity L divided by mu. Okay, so wherever Rex is written, that means rho u infinity x by mu. X represents the location where you want to calculate the Reynolds number. Okay. So shear stress formula, you can note this particular formula. Shear stress formula for flow over a flat plate, or the Blasius found this equation for shear stress at wall. You see, shear stress will be, he has calculated shear stress at the wall, not at any other location, not at any other. This equation is only applicable at the wall, and they will ask at wall only. They are not going to ask away from the wall. Okay, so even gate doesn't ask, that is not there in your syllabus. Okay, so uh, they are only going to ask what is the shear stress at the wall. So this is the equation, and if you know shear stress, you can calculate the skin friction coefficient. See, last lecture I have told you two things are there. One is friction factor, Darcy friction factor, and one is skin friction coefficient, which is CFX. So if this is my plate, the friction coefficient, this is my plate, so in x direction the friction coefficient can change. At different location, different friction coefficient can be there. So that friction coefficient, if you want to calculate, you can calculate with the help of this formula. CFX is equals to 0.664 divided by root over REX. Now again, if you see, it is here it is REX. At any x location, you will get skin friction coefficient at any x location. So at any x location, you can calculate shear stress. At any x location, you can calculate CFX. So you can note this thing, this and this. So in this particular slide, the important points what we have covered is pressure, related to pressure gradient, dou P by dou X, dou P by dou X, pressure gradient in X direction, it is 0. Pressure is constant. This is the first thing. Second is boundary condition for flat plate or a flow or a flat plate. Third is Blasius equation, its order and whether it is linear or non-linear. So it is third order and non-linear equation. Then another is equation for shear stress at the wall, equation for at any location, obviously at any location, and skin friction coefficient at the wall or of the plate at any location. Done. Okay. Now this is at any x location. We can calculate the average value also. The average value of that also we can calculate. So these things we see when this is the derivation of that, how we are getting the Blase's equation. You see that it is third order non-linear equation, and it is ordinary differential equation. Okay, this is third order non-linear ordinary differential equation. It's not they have asked this also, that whether it is partial differential equation, ordinary differential equation, or like that they have asked these things. Okay, so this is our ordinary differential equation. So third order non-linear ordinary differential equation. So this is the derivation which you don't have to study right now. Now we have seen the formula for shear stress at the wall. We have seen formula for skin friction coefficient of the plate. Now we can and that too at any x location. Now we can calculate the force. Like you see, when a fluid is flowing over a plate, the fluid is flowing like this, it will exert a force on this plate in this direction. As it is moving in this direction, it will exert a force, obviously, in this direction. So how much force it is exerting in this direction? Okay, so that you can calculate. How you can calculate force is what? Shear stress at the wall multiplied by area. Like force is what? Pressure multiplied by area. Here at the wall, due to shear stress, it is having this friction force. Okay, on the flat plate. So shear stress multiplied by area will give you the force over that plate. Okay, so shear stress. Now area can be written as, you see, this is my flat plate. Okay, now if this is my plate like this, the unit depth is 1 unit, and this is, let's say, some L. Now I will first take a element like this whose length is dx. Length of this element is dx. So over this small area, what is the force? So over this small area, the force is shear stress at this location. Shear stress at this location multiply area of this width, area of this strip, which is dx multiplied by 1. Now total force from here to here, what you will do? You will integrate it from 0, x equals to 0 to x equals to L. So you will have to integrate from x equals to 0 to L. With this, you will get the force over a plate, force over a flat plate, and this is the equation what you will get. Okay, so here if you see, last slide we have seen the equation was like for skin this not skin friction coefficient, the shear stress equation. Shear stress, it is 0.332 rho u free t square divided by root over rex. So you will have to integrate this one with dx, and you will get the relation. Okay. Okay, one more thing is there. Okay, this we'll see in next slide. It is there. Okay, so force over a flat plate, this is how you can calculate. Okay, I think uh, this you just check in the book also, the equation force over total friction force per unit width on a flat plate. You can check this particular factor. It may be either it is 0.664 or 1.328. You just check this one, but I think it is this only. But just check this one once, or you can integrate this one and you will get the result. Okay, now uh, means last slide we have seen skin friction coefficient, CFX. This was what? 0.664, then root over rex. This is skin friction coefficient at any location x. But if you want to calculate average skin friction coefficient, you will have to integrate it from 0 to L. When you integrate this one, it will become 2 times. When it will become 2 times, you'll get, you see 0.664 multiplied by 2, you'll get 1.328 divided by root over REL now. Now it will become REL. Okay, so REL means rho u infinity L by mu. REX is rho u infinity X by mu. Okay. Now, so this you can, if you remember skin friction coefficient equation at any X location, you just multiply by 2, you will get the average value. Okay. Now, another point is, what is the equation for boundary layer thickness at any location? Like if this is my plate, and this is important, this is my plate and this is my boundary layer. This is my boundary layer. Now, and this is the thickness of boundary layer, which is increasing in X direction. So delta is function of X. Delta is function of X. Skin, this boundary layer thickness. Okay. Now, the formula what he have derived is, what is boundary layer thickness? Where u by u infinity is 0.99. This I have already explained. What is boundary layer thickness? This is the boundary layer thickness, delta, this height. Now, this height is at this point, u by u infinity, where you will get u by u infinity is 0.99, or u is equals to 0.99 times u infinity. That height is boundary layer thickness. Okay. And this thickness delta x is given as 5x by root over Rex. Okay, the value for this boundary layer thickness is 5x by root over Rex. So they can ask, what is the equation for boundary layer thickness in case of what? Blassius solution. This is applicable for Blassius solution. For other cases, this factor changes actually. This 5 can change from 5 to 4.6, 4.5, 4.8, something like that. It changes. Okay, for other cases. For Blassius solution, it is 5x by root over Rex. So from here, we can conclude that boundary layer thickness varies with X, and that too with root over X. You see, delta is varying, it is proportional to root over X. So you can say, sir, delta X is proportional to X. It is not proportional to root X. You see, you are just focusing on this X. But here also one X is there, no? It is like 5x divided by root over Rex. Now Rex is rho u infinity X by mu. Now this root X and this X. So this will cancel out. So I will get 5 root X divided by rho u infinity by mu. This is the equation what I am getting here. So it is proportional to root over X. Okay. So boundary layer thickness delta X is proportional to root over X. Okay, so this is the important point you can note. This one, and average value, you can remember it is 2 times only, and how to calculate force is over this one, but I don't think they are going to ask you to calculate force over a flat plate. It will take time. So I don't think they are going to ask you. Just for your knowledge, I'm telling you, but this they can ask. Average friction coefficient value or equation, and how the boundary layer thickness varies. They can give you like this. If this is my this is my boundary layer. So let's say at x equals to 1 meter, boundary layer thickness is 1 mm. Now what will be the boundary layer thickness at x equals to 2 meter? So they can ask you like this. So you know delta x is proportional to root over x. So delta 1 by delta 2 is equals to root over x1 by root over x2. Okay. So delta 1 is what? 1 mm. This is 1 mm divided by delta 2. You have to calculate, equals to root over x1. X1 is 1 meter. Okay. 1 meter. And this is root over 2. So from here you can calculate your delta 2. Okay. Like this they can ask. In GATE they have asked so many times. So they can ask here also. They can give some values which you can calculate quickly. Clear? Shall I move to next slide? Let me know when you are done. And this you check, it comes 1.3208 only. You can integrate and check, but just confirm with book one time. You can confirm with the book also. You can once you can confirm this one. I think it is 1.328 only. Now, next is few more points only. Few more points, and then we're done with boundary layer thickness. But these points or the equations what I'm going to tell you, it is important. They can ask directly in the examination. Okay. In fact, equation they can ask. Okay. The derivation part is not that important, but remembering the equation is important here. But okay, we'll see with the definition also, we'll see these things. Now we are going to study about displacement thickness, momentum thickness, and energy thickness. What is this? The displacement thickness. You see, this is my flat plate. This is my flat plate. And fluid is entering with some uniform velocity u here. Okay. Now, you see, because of this boundary layer, the fluid, you see, it was entering horizontally. All layers were entering horizontally, but because of this boundary layer, there is a reduction of flow in this inside the boundary layer or near to the wall. So the flow now shifts actually. The flow shifts in this direction. So actually the flow should be within this line. It should be within this line because it has entered like this. Up to this height only it has entered. So it has entered with a height of h. Okay. But because of this boundary layer, the flow is shifted here. It shift like this. It has shifted like this. So how much at any location? Let's say if I talk about this location, if I talk at this location, this is the boundary layer thickness. This is not boundary layer thickness. This much height is, it has shifted. So if it has shifted this much, so this is the, or I can say it has displaced this layer. This layer has displaced by this amount at this particular location. So this is your displacement thickness. Okay. How much the external potential flow shift outwards due to formation of boundary layer. If this boundary layer is not there, no, this shift will not happen. So because of this boundary layer only, this shift is happening. So this represents the displacement thickness. Okay, displacement thickness. So do you understand the meaning of displacement thickness? Okay. Now to get the formula for that, simply what we will have to do is the continuity equation we can apply. Okay, continuity equation we can apply and we'll get. So we can apply the mass which is entering here, the flow or the volume flow rate which is entering here. Okay, so how it is entering with which velocity? U velocity, U infinity velocity. Height is h. Let's say depth is 1 meter. This depth I will call as 1. So the area, this particular area with which the fluid is entering here, the area will be what? Height multiplied by 1. So what is volume flow rate? Volume flow rate will be area multiplied by velocity. Now area is what? Height multiplied by 1. And velocity is what? U infinity. So this is the volume flow rate. U infinity multiplied by h. This is the volume flow rate with which it is entering here at this location. It is entering. Is this thing clear? It is entering with this volume flow rate. Okay. Now at this location also the volume flow rate should remain same. It cannot change. It should remain same here. Okay. So you see up to this height, means this is your boundary layer. So if I consider this point below this height, the velocity is function of y. It is varying in y direction because velocity profile will be what? If you see the velocity profile here will be something like this, and then it will become vertical, almost vertical. So in this direction, after this, outside the boundary layer, the velocity is not changing. But inside the boundary layer from here to here, it is changing. It is 0 here and it is u infinity here, 0.99 u infinity here. Okay. So inside the boundary layer, it is changing. So if I want to calculate the volume flow rate at this location, again I will have to apply that volume flow rate, which is area multiplied by u only, area multiplied by this u velocity only. But I will have to divide it into two part actually. I will have to divide it into two part. Let's say I will divide like this part and above this part. Below this part, small portion of this also outside the boundary layer also have considered here. That doesn't make any difference. I just want to see this. I just want to take means I want to consider this thickness in my equation. Okay, I want to take this particular thing in my equation actually. That's why I've divided above this with which it has entered. So below this one height and above this another height. Now from here to here, if you see, it is varying. U is function of y. Okay, u is function of y. But outside this, u is u infinity. So I will have to calculate volume flow rate in two parts. First, below this, how much fluid is moving, and above this, how much fluid is moving. So above this, if I see, it will be area multiplied by velocity. Area will be what? This height, delta S star, multiplied by unit width, multiplied by velocity, which is u infinity only. Outside it is u infinity. Plus, if I consider this one inside the boundary layer, plus, now this height I don't know. So I will have to consider some small element here whose height is dy like this. Then area will be dy multiplied by 1 for this small height only, small strip only. And velocity is what? U, a variable velocity u. And then I will have to integrate it from 0 to this much height h. Okay. So this is equals to the volume flow rate with which it has entered, which is h equals to u infinity. Okay. This is the equation. This is how we can uh, equate the volume flow rate at two locations. One is this location and one is this location. If we equate this two, no, if we equate this two, will get and then rearrange. You see, simply this is equals to this plus this I have written. Then I have taken this left hand side. I can write like 0 to h u infinity dy. I can write like if I integrate this one, what I will get? U infinity, and integration of dy is y. Limit 0 to h, so I will get h only. So u infinity into h. So I have forcefully written this particular thing like this. Okay. So I am getting this thing, then right hand side like this only, this is this only. And then after rearrangement, and I want to calculate what? Delta star. So I will keep this particular term in left hand side, other things I will take in right hand side. And after rearrangement, I will get this particular equation. This equation you will have to remember. This equation is equation for displacement thickness. This equation is equation for displacement thickness. So you should remember this equation. Similarly, momentum thickness. There is a shift. So because of this shift, or there is a because there is a viscous effect inside the boundary layer. Because of this friction, there will be a loss of momentum. If there is a loss of there will be a loss of momentum, and there will be a loss of energy. So we'll calculate both. First, we'll see the momentum. So to calculate the loss of momentum, again we'll have to balance the momentum. Momentum at this location, momentum this location. The difference of these two will tell you the loss of momentum. Okay, and that much amount you will have to shift. Your flow should shift that much amount. Like let's say theta. Theta represents momentum thickness. So you will have to shift your flow by theta so that you can overcome your this momentum loss. Okay, so again you can balance, you can calculate momentum at this location, you can calculate momentum at this location and take the difference. Obviously both will not be same, because this location momentum will be more, here there will be this one be reduced one, because there will be a loss of some momentum. You take the difference, the equation what you will get is this thing. This represents what? Momentum thickness. This represents momentum thickness. Okay, so this equation also you will have to remember. You see, if you remember this thing, you simply multiply u by u infinity here, you'll get momentum thickness. Now the energy thickness, again same thing, here and here we'll calculate the energy. And similar way you can take the screenshot and you can read the equation. It is similar, it is in similar fashion it is written. So energy also you can see here and here. You calculate and take the difference. The difference will tell you the loss of energy, that much you will have to shift. So the energy thickness, will be, now you again square, you just square of take a square of this ratio u by infinity inside this one. So you see our this one delta star, which is delta star only, no, this one, delta star, which is our displacement thickness. Displacement thickness was 1 minus u by u infinity. Okay, 0 to delta. Momentum thickness was same thing, only thing you multiply u by infinity outside this bracket, 1 minus u by u infinity. Okay, then energy thickness delta E, you square this thing, it will become 0 delta u by u infinity. Okay, 1 minus u by u infinity is there, already there, just make a square of this one, calculate the square of this one. This will represent energy thickness, this is momentum thickness, this is your displacement thickness. So you should remember all three equations. Let me know when you are done. With this, your boundary layer thickness is completed. Boundary layer theory is completed. Okay, one more question they can ask: how the boundary layer separates? the boundary layer can separate also. So this is the last topic. That boundary layer theory is completed. Now this is a flow separation. So this is last one actually. Okay, this is last one. So separation of boundary layer. So what happens in a nozzle, like this is my nozzle, and so this is nozzle part and this is diffuser part. Okay, so this is nozzle, this is throat, and this is diffuser. What happens? You see, when fluid is flowing in this direction, velocity is increasing and pressure is reducing. Velocity increases, pressure reduces. With the help of Bernoulli's equation, you can explain this thing. So when it is convergent, velocity increases. Why velocity increases? To maintain the mass flow rate, okay, or volume flow rate. So volume flow rate is area multiplied by velocity. So if area is reducing, velocity has to increase to make discharge constant. Okay, so that's why when area is reducing, the velocity has to increase. Okay, so you see, in this direction velocity increases, and now with the help of Bernoulli's equation we can explain that in this direction pressure reduces, because Bernoulli's equation is P by rho g plus V square by 2g plus Z is equals to constant. Height is not considered here because that we can leave. That variation is not there much for two different location. So P by rho g plus V square by 2g. Now this is not zero, this is some constant. Okay, now if velocity is increasing, then this has to reduce. If this term is increasing, velocity is increasing, with this term is increasing, value of this term is increasing, then this has to reduce to keep this thing constant. That's why in nozzle, when so with the help of continuity you are explaining that in this direction velocity will increase. Now with the help of Bernoulli's equation you are explaining that in this direction with increase in velocity pressure will reduce. Okay, and if area is constant, which is at the throat, the velocity and pressure will remain same. Now coming to diffuser part, you see the area is increasing. If area is increasing, velocity has to reduce, so velocity will reduce. If velocity is reducing, pressure has to increase. Now you see, this represents, now fluid is moving in this direction. Fluid is moving in this direction. Pressure here, I will take it as P1. This I will take it as P2. Now, pressure at 1 is more than pressure at 2. So this thing is helping. This gradient is negative, no? Negative pressure gradient, which is a favorable pressure gradient. I have explained in last lecture. So negative pressure gradient, P2 minus P1 is negative. So favorable pressure gradient. So it is helping the fluid in moving in the, helping the fluid to move in this direction. But if I consider beyond this point, fluid is moving in this direction. But if I take, let's say this is my P3 and this is my P4, P4 is greater than P3. So P4 minus P3 is positive. So it is adverse pressure gradient. So when fluid is moving in this direction, this pressure will oppose the flow. It will oppose the flow. If this pressure gradient is so large that the inertia will not help to overcome this pressure thing, and one more force is there at the wall, there will be a boundary layer and there will be a significant viscous forces. So viscous force is acting at, if I talk about this point, in opposite direction viscous force is there, force due to viscosity is there, and in opposite direction force due to pressure is there, and in this direction only force due to your inertia is there. Okay, force due to inertia is there. So inertia force is being opposed by two forces, viscous force and pressure force. If this two force is so large compared to inertia that if it is opposing the flow, then what happens? Locally near the wall, the fluid reverses. Fluid flow reverses, or back flow happens. Back flow happens like this. Okay, and the boundary layer separates. The boundary layer separates. Why the boundary layer separating? Because of this phenomena, because of this opposition of flow. Okay, so what is responsible? The adverse pressure gradient is responsible for this one. Adverse pressure gradient, and obviously the viscous effect is in opposite direction only. So in this case, pressure is favorable. So here in nozzle case, you will not have flow separation. This is the first point in this topic. Under this topic, separation of boundary layer, you can note that flow separation will not take place in nozzle part. Flow separation will always take place in divergent part, not in nozzle, not in throat. It will always take place in which part? Divergent part. This is the first point you can note. Now, next is where the separation takes place. Some students have this doubt that when dp by dx is greater than 0, sorry, less than 0, your separation takes place. No. See, separation will, you see, in this at this location, beyond this point, diffuser is started. Diffuser has started. Okay. So at this point, if you see, the diffuser part is there, but flow separation is not happening. Here, if you see at this location, if you see dp by dx, it is less than 0. Sorry, not less than 0. Yeah. Sorry. Here it is more, no? P4 minus P3. So P4 minus P3 greater than 0. Positive. Okay. Adverse pressure gradient. Positive. So here also there is an adverse pressure gradient. But flow has not separated. It has started. The effect has started. When both means here still inertia is having that much the fluid is having that much inertia to overcome this particular this force, overcome this pressure force or viscous force. Okay, but this pressure force and viscous force keeps on increasing in this direction, inertia and it is continuously opposing the inertia flow. So at some point what happens, this becomes, this two will become equal, and after that this two viscous and pressure force will be more and inertia will be less, and then the separation happens. So it is not you cannot write like a deep, when dp by dx is greater than 0, then only separation happens. No, this is not the condition. Pressure increase of pressure gradient or the adverse pressure gradient is responsible, but mathematically that is not, this is not less than 0, this is greater than 0. dp by dx greater than 0 is not the point where separation happens. Separation happens at this point, where dou u by dou y at y equals to 0 is 0, and not this one. Sometimes they have asked this question, they have given this in your options: dp by dx less than 0, dp by dx greater than 0, equals to 0, and only one of this will be given. Dou u by dou y at y equals to 0 is 0. This is the answer, and not this dp. dp by dx is not mathematically, it will explain where this thing is means flow separation takes place. Flow separation will take place at a location where dou u by dou y at y equals to 0 is 0. So please make up note of this point. Okay. Now, when the flow is like, this is my cylinder, when the flow, this flow is laminar, when the flow is laminar, and this is my theta at any location theta, this is 90 degree, this is more than 90 degree. So where the separation will happen? If flow is flow is occurring over a cylinder, then where the, at what location the flow, this separation will happen? You see, separation for, if it is laminar flow, the separation will be little lesser than theta equals to 90 degree. And if it is turbulent flow, it will have higher energy, so the separation will happen beyond 90 degree, beyond 90 degree. Okay. So for laminar boundary layer, experimentally it was seen, flow over a sphere. For laminar boundary layer, the separation will take place around 82 degree or 85 degree. For turbulent boundary layer, the flow separation will happen at more than 90 degree, which is around 125 degree centigrade. So you can make a note of this one also. And in laminar flow, you will have more drag. In turbulent flow, you will have less drag. This point also you note down. Over this one, done. Okay, so this boundary layer is over now. You can solve this question. So laminar boundary layer occurs over a flat plate at zero incident to flow. Okay, the thickness of boundary layer at section 2 meter is 2 mm. I have already explained na this question. Delta is proportional to root x. So delta 1 by delta 2 is equals to root over x1 by root over x2. So 2 meter at 2 mm means 2 mm at 2 meter. So 2 mm by delta 2 you have to calculate root over, this is 2 meter, divide by, you want to calculate at 4 meter, this is 4. Okay, so delta 2 is 2. This will become on this one, just root 2 by root 4, which is 2. Then this will become root 2. So 2 root 2. This is the answer. Clear? Next question, 481. Yes, C, less than inertia force. Four 77. It is boundary layer thickness y equals to delta, u is equals to 0.9 and u infinity. Displacement thickness, this only. Momentum thickness, you multiply u by u infinity here, which is this only, and then you multiply u by infinity here, so it will give, you will give energy thickness. So all are corresponding only. So 1, 2, 3, 4, A option. Okay, now one more thing. This particular thing I'm going like numbers. There are this flow numbers are there, like Reynolds number, RE, Reynolds number, which is inertia force by viscous force. Okay, then there is Euler's number. It is related to inertia force and pressure force. Okay, then there is a Froude number. It is related to your, here see everywhere it is inertia only, this things actually changes. So Froude number, it is related to your gravity. Okay, Froude number related to your gravity. Then Mach number, which is your actual speed by speed of sound. So it is related to your elastic force. These numbers are very, means definition is very important actually. Okay, and then Weber number. Weber number, it is related to surface tension. Okay, you just read this the definitions of this number. It is very important actually. They can ask you in examination like this, just match which number represents what. So you see Weber number, if we start with the Weber number, it is related to surface tension. Okay, it is related to surface tension. So D ka 4. Okay, now Mach number, it is related to elastic force. Okay, so C ka 5. Okay, then Froude number related to gravity, so 2, and Euler number related to pressure force, 1. So D is the option. Okay, definition you just. So with this, we have completed our fluid mechanics. Only thing, there is this turbulent flow. Okay, turbulent flow. I don't think they are going to ask, and means because there are all experimental results, experimental equations are there. Uh, Questions they may not ask. Only thing they might ask related to the this number. When the Reynolds number is greater than 4,000, then it becomes turbulent flow in case of pipe. In case of your flow over a flat plate, it is order of 10 to power 7. Beyond that, it will be turbulent flow. Like that, they can ask. Okay, and uh, this laminar flow, you see, in laminar flow, the layer glides over each other. So if there is one particle standing here, it will not, means it flowing in this direction, it will not move to immediate or next layer. It will not travel in this direction, or mixing will never happen in this case. Okay, it will always move in this direction only. Okay, so here in laminar flow, which is also and this will happen when viscosity is very high. When viscous flow is there, one layer glides over another layer. Okay, so mixing will not happen in this case. Mixing will not happen. But in turbulent flow, what happens, if different layers are there, this molecule is there, this will travel here, mixing, so much mixing will be there. Okay, so this is, and this happens when uh, this particular thing happens because it is having high inertia. It is having high inertia, or high energy, or it is having higher velocity. If it having higher velocity, it will jump to next layer, or this layer or this layer, and mixing will happen. But in case of laminar flow, viscosity is higher, no, and it is having lesser inertia. You see, Reynolds number is inertia by viscous force. If viscous is higher, Reynolds number will be lesser. Okay, so, and if Reynolds number is lesser, it is laminar flow. Okay, so if it is viscous, it is laminar, and it will glide over each other. So mixing will not happen. For turbulent flow, inertia is higher than viscous. Okay, inertia is very high, so molecule have sufficient velocity, so mixing will happen. This is the thing they can ask here. Okay, otherwise, and one more thing, uh, like your profile. One more thing, this is also important only, like this velocity profile. Like if this is my pipeline, okay, the velocity profile, if it is laminar, is what? Parabolic, like this. It is maximum at the center, and zero here. But if it is turbulent, the flow is more uniform. It seems like if it is turbulent, no, it is not uniform. The word itself tells it signifies that turbulent, no, it will not be uniform, but it is uniform. Why? Because of mixing only it is uniform. You see, its profile will be something like this. This will be almost flat only. Why so? Because you see here the velocity is continuously changing. Why? This molecule is not trying to shift to nearby layer. But in this case, what happens, if this molecule is there, no, it will shift here. So it will increase this velocity. Then it will shift here. It will increase this velocity. So what it could be something like this. So at this location, its velocity could have been lesser, but because of movement of this velocity in this direction, the velocity has increases. So because of that, it is more uniform. So the velocity profile is more uniform in case of turbulent flow compared to your laminar flow. So this is also one important point you can note. Okay. And please solve these questions are from RK Jain book only. RK Jain book objective questions. Like we have solved almost, I think, more than 300 questions we would have solved, I think. Okay, so and few questions are remaining. You can solve those questions also, or for other subjects also you can refer this book if you have time. You can refer at least some questions you can solve for every topic. 400 plus questions are given in this book, so you can get PDF. If you don't find, you just let me know, we'll see. Okay, so with this we'll end our fluid mechanics class, and I will end the class now. Thank you, all the best.